Okay, so today we will start with some very important concepts of oscillations. So we will discuss three different types of oscillations. One is the free oscillation, and then the damped oscillation, and then the forced oscillation.
Hmm.
So these three are very important oscillations. So let us start with that one by one.
Hmm.
So first we will look at free oscillation, concept of free oscillation. So as the name suggests, free oscillation is that oscillation which occurs naturally. So there are several types of oscillations which occur naturally,
Hmm.
or we just have to give it a small trigger and it will keep on oscillating naturally. Like the pendulum example is a very popular example. Pendulum, if you just give it a trigger and it will keep on oscillating about its mean position. The spring, the mass spring block, so that also keeps on oscillating. So here it is the concept of free oscillation.
Hmm.
Now in the free oscillation, the mathematical aspect of it, the frequency of the free oscillation is this. So frequency of the free oscillation is 1 upon 2 pi. I will write it. Frequency of free oscillation. Because in the numericals, they will ask only these things. Natural frequency, frequency of free oscillation, time. If we know the frequency, time period, we can calculate. So frequency of free oscillations. So I am calling it F. It is equal to 1 upon 2 pi under root of G by L, where G is the acceleration due to gravity, L is the length. And this is the frequency of free oscillation of oscillating pendulum. So this is the case for pendulum. So as we can see, in the case of pendulum, the frequency depends on the length, and it is very important. And it is sort of inversely proportional to the length. Frequency means number of oscillations per second. So if I increase the length of the pendulum, number of oscillations per second will decrease. It will take more time to complete one cycle. And very important observation, the frequency of oscillation is independent of mass. Very important. Because in this equation, there is no mass. So I can say that
it depends on length. Yeah.
It only depends on the length. So
and then greater the length, less the
frequency.
Speed. Yeah.
Greater the length, the more it will take, the more time taken by it to complete the cycle.
And that is because of torque. Like if there is torque, or what do you call that, sir? Like the longer the string is in the rotational, I forgot the exact term, but yeah.
So torque, so it is applicable for a rigid body, solid rigid body. Here we have a very thin string. We consider it to be massless.
That's right.
Yeah, but definitely some other phenomena is working. That is for sure. But it is very clear to us that okay, frequency of free oscillation of a simple pendulum, it is inversely proportional to the length.
Okay.
And one more very interesting thing, like if there is no resisting force, then it will keep on oscillating forever. And this is a very important property of oscillations. It can keep on oscillating forever if there is no resistive forces. And this frequency of free oscillation, this frequency we call it as natural frequency. This frequency we give it the name as the natural frequency. So when in the free oscillation, we always have the natural frequency. And for different systems, the natural frequency will be different. For pendulum, this is the natural frequency. For spring block system, the natural frequency will be different. Or for any other free oscillation, the natural frequency, we have to derive it according to that context. And we call it the ideal oscillator. Like the oscillator oscillating with natural frequency, that is the ideal oscillator. It is not experiencing any resistive forces. Now, one more very important property I will write. Because these properties, very small properties, but very important. We have to no time limit. Time period of oscillation. Time period of oscillation, like natural oscillation, free oscillation of an ideal oscillator. So the time period of oscillation of an ideal oscillator, it depends, like it is independent of amplitude. Independent of the amplitude. And it depends only on the characteristic property. It depends only on the characteristic property of the oscillation. So this is very clear. So in an ideal oscillator, the total energy and the amplitude remains constant. So this is the ideal oscillator. Total energy is constant, conserved, amplitude is constant. Amplitude is Now let us look at one numerical, like a few numericals. We will do two numericals. Then we will go to the next topic to get an idea.
What about the derivations?
Here, no need for derivation.
Okay.
Because in the numerical only we will get an idea.
Okay.
Yeah. Because here in this topic you can expect numericals for sure. So let us do that. A question: a body of mass 4.9 kilogram hangs from a spring and oscillates with a period of 0.6 seconds. With a period of 0.6 seconds. How much will be spring shorten when the body is removed? So the question is that a body of mass 4.9 kilogram hangs from a spring and it is oscillating. It's already the spring block system, the spring mass system, the vertical, it is already undergoing an oscillation. Time period is given 0.6 seconds. Now we have to find how much will be the spring shorten when the body is removed. So definitely when the body is removed, the spring will compress to its maximum, and that we can call it the amplitude. So that we have to find.
Yes, sir.
So this is the vertical spring mass system. This is the mass, which is the 4.9 kg, and it is already undergoing a oscillatory motion, and the time period is given. How much will be the spring shorten? So we have already seen in one of the formulas, we have already seen that time period in an oscillatory motion, it is 2 pi under root of m by k. The k is the spring constant and m is the mass. And this formula is for spring block system or spring mass system. So for spring mass system, we have the time period given by this formula. So time period is equal to 2 pi under root of m by k, where m is the mass attached with the spring and k is the spring constant. Now, in this equation, we know two quantities. We know the mass, we know the time period. And from here, we can calculate the spring constant. So let us do that. So I can do some reshuffling. So I can say that 0.6 seconds is equal to 2 pi under root of n by k, 4.9. And when we will solve this, we will get k. Okay, k will be 536.8. 536.8 Newton. Okay, so now we are able to calculate the spring constant, but ultimately what we have to calculate the displacement or the maximum displacement during the compression, because when the block is removed, it will compress to its maximum, like the spring will shorten. That we have to calculate. Now we also know that in this spring block system, there is a restoring force which is responsible for the oscillation. And that restoring force, we know it is F is equal to minus Kx, where minus represents the sign, like it is opposite direction. So I can just write F is equal to Kx. So restoring force, capital F is equal to K. From here I can write X will be F by K. Now we know that in the vertical spring mass system, it is experiencing a force mg, and the restoring force is acting opposite direction. So the restoring force is equal to the mg force, because of which it is balanced. So the restoring force is mass into that acceleration due to gravity. I can write it. What is the mass? 4.9. Acceleration due to gravity 9.8. Upon spring constant we already calculated, that is 536.8. And from this I will get the final answer after simplifying this, that is 0.089 meter, or I can write it 8.9 centimeters. So this is the answer.
Okay. So just give me a second, I'll just write it. Okay, done.
Now we will go to the next question.
So just write the question, I'll be back.
Question is mass m is equal to 2 kilogram hangs from a vertical spring. A mass is hanging from a vertical spring when a mass small m is equal to 0.6 kilogram is gently added. The spring is further stretched. The spring is further stretched by 4 centimeters. Now m is removed. Now M is removed, capital M is set into the oscillation. What we have to do, we have to calculate the period of oscillation. Calculate the period of. Let us look at the question. In the question, a mass 2 kilogram hangs from a vertical spring. So let us visualize this. We have a vertical spring. A mass is attached with it, 2 kilogram. So this mass hangs, and an additional mass of 0.6 kg is added. Let us suppose we add an additional mass of 0.6 kg into the system. Small m is equal to 0.6 kg. The spring is further stretched by 4 centimeters. So after addition of the mass, the spring gets stretched. Additional displacement will be 4 centimeters. And now the mass m is removed and capital M is set into oscillation. Calculate the period of oscillations. Yeah, so it is looking a bit complex, but it is very easy.
First we do with combined weight, like we add them together, then we subtract.
Yeah. So now what we will do first, we have to see step by step. We have to do the first scenario. We only have capital M mass because small m mass is added after some time. In the first scenario, only capital M mass is there. So first analyze the first scenario. In the first scenario, for the system, F is equal to like minus kx. So the mass is only 2 kilogram. So I can write F is equal to kx. So spring constant is not given here, but I know that here F is the mg. I can write mg is equal to kx, and mass is 2. I can write 2g is equal to kx. So this is the first scenario. I got one equation for it. In the second scenario, I will increase the mass. I will add an additional mass. So in the second scenario, the total mass will increase and displacement will also increase. So the same equation, it will become mg, that is 2 plus 0.6. Or first let me write the equation, then substitute the value. So the equation, the total mass will be m plus small m into g, x plus 4. And we have to be very careful, like since the mass is in kilogram, let us convert this centimeter into meter here itself. Otherwise we will forget and the question will go. It is in meter. Now, this is very clear to us. Now we can substitute values. So we will get 2 plus 0.6. So 2.6 g is equal to k times x plus 0. Now we have two equations. This is the equation 1 and equation 2. And now we can very easily solve these both equations to get the spring constant. And once we got the spring constant, then definitely we will be in a good position to calculate the time period of the oscillation. So let us give it a try. So here I can say that the solving 1 and because here instead of kx I can add 2g or something like that. Or instead of x I can add 2g by k and I can get the k. So ultimately after solving this we will get k is equal to 0.6 into 9.8 upon 0.0. That will be 14.7 Newton per meter. So this is clear to us. Now, once we have the K, we know that for the vertical spring mass system, we know the formula for time period or period of oscillation, which we have to calculate. Period of oscillation, which we have to calculate. That I can call it capital T, 2 pi under root of m by k. And we have to find the period of oscillation after the block is removed, small m is removed. So the only mass we will be having is the capital M. And if we substitute values, we will get 2 pi under root of 2 by 14.7. So we get 2.317 seconds. It is the answer.
So just a second, I'll write it down. Yeah.
Now we will look at the next concept, that is the damped oscillation. Like we know its meaning, but like mathematically, we will analyze the damped oscillations, and it's very important. Damped oscillations. So we know that in the real world, the world which we are living, here nothing is ideal because there is a friction, and because of that, everything fades. There is a continuous loss in energy, and oscillation also, it will fade away after some time. So real world, there is always a decrease in amplitude with time. Amplitude is not constant, but amplitude is continuously decreasing with time.
Okay.
We can visualize it very easily.
Hmm.
Well, let us suppose this is the initial amplitude, and after, like with the time, it will decrease. The amplitude will, and it will fade.
Hmm.
So this is the damped oscillation. So this is the time. This is the displacement.
Hmm.
Fading of that. And what is the responsible for that? Frictional force, which is always there.
Hmm.
And hence there is a loss of energy.
Hmm.
So I will write some definition for this damped oscillation. So I can say that the phenomenon of decay, the phenomenon of decay in the amplitude, the phenomenon of decay in the amplitude of oscillations. It is the damped oscillations. It's the damped oscillations. And definitely in the damped oscillation, there will be a time instant where the amplitude will become zero, as we can see in the graph also.
Hmm.
And amplitude, like a damped oscillation, they are not sinusoidal because
yeah, it reduces.
It is reduced.
But
It's understood.
What is it called then?
No name for this, or we can just call it like damped oscillation.
Okay.
Continuously it is damping.
Hmm.
Okay, it's clear. Now here, the time period, it depends on the amplitude. That we will derive equation, then it will be clear. So here basically let us do the mathematics now.
Okay.
Like derivation for this damped oscillation. So the idea is that we know that what is the main reason for the oscillatory motion? The main reason for the oscillatory motion is the restoring force. Restoring force is the force acting in the opposite direction, which is trying to pull the body towards the mean position. That is the restoring force. In the real world, along with the restoring force, resistive force is also acting, and that is the reason for the damped oscillation. So whatever derivation we did earlier, the same process we will follow, just that we will include that additional resistive force. Then
so talking about natural resistance, or we are providing this is both.
Here we can consider the natural resistance itself.
Only the natural resistance.
Only the natural resistance, like the resistance caused by the air, or if it is on the surface, the spring blocks system.
What about the resistance that we give?
Yeah, so if we are giving some additional force also, we have to add that.
Damp, but it falls under the damp.
Yeah, it will fall under the damp, and we have to add it.
Okay.
Along with the restoring.
Yeah, like adding water on the spring, so it becomes rusted or something like that.
Yeah. Okay. So let us do the derivation. F is the restoring force, and F dash is the resistive force. And this F dash can be a sum of different small forces also, as you mentioned. So we can collectively call them F dash.
Okay.
And we know that restoring force is minus Kx. Where K is the spring constant, X is the displacement. And we are calling the resistive force as minus Pv. Minus because resistive force is also acting in the opposite direction. That's a minus. V is any constant, and V. Okay. And V is the velocity. Because this resistance, it depends on the velocity. So the faster the body is moving, the more the resistive force it will experience. Isn't it?
Yes, sir.
Now, according to the Newton's laws of motion, the total force acting in a body, the total force acting on a body is always mass into acceleration. That is the Newton's laws of second law of motion. So this combined force, because the mass is same, because these combined forces, they are acting on the same body, same object, the mass is same, and the acceleration produced by these combined forces, I can take it A. So I can say that ma is equal to minus kx minus bv, isn't it? Now here, what I can do is this ma, this is the net force, I can say.
So one second, what is VB again?
Okay, so VB is the resistive force. So see, resistive force is also opposing in nature, and hence minus is there. Small b is any constant. It is a constant, and v is the velocity with which the object is moving.
Okay, got it.
It is been seen that if a body is moving fast moving object, they experience more resistive force, and this is the restoring force. This is the restoring. And this term, along with the minus sign, this term, it is that we call it the damping force. is the damping. It is responsible for this damping behavior. Okay. Now we can do some mathematics around it, because now we got a equation and we can play with that. So I can write it like this. Mass is a constant. I can write it as it is. Acceleration, I know it is the double derivative of the displacement, d2x by dt square minus kx. And velocity, I know it is dx by dt. Velocity is dx by dt. Now I can take all the terms to the left hand side. I will get an equation something like this: m d square x by dt square plus kx plus b dx by dt. It is equal to, isn't it?
Yes, sir.
Now I can further refine it, because I am trying to make a differential equation of second order. Okay, so let us try that. So I'm dividing both the side with mass n. I will get d2x upon dt square plus k by m x plus b by m dx by d. And how I got it? Dividing both sides by. Dividing both sides by. Now what I will do, see, k is a constant, m is also constant. So k by m will be a constant and b by m will be a constant. So we will introduce that. So finally I will get a standard equation, that is the equation for this damped oscillation. Very important it is. d2x dt square plus, I will introduce this constant. K by m, I am calling it like the damping coefficient. It's the damping coefficient. And b by m. Okay, so b by m is the damping coefficient. I can write it like this. Dx. So b by m is the damping coefficient, and k by m, that is the natural, under root of k by m is the natural frequency of the system. So I can write it omega naught square. Omega naught x. I will mention it here, whatever I have taken. So here the damping coefficient, gamma is equal to b by m, and also
sorry,
the natural frequency.
In the previous step, is it dividing both sides by m, dividing both sides by 0?
Oh, sorry. It's a typo. It is dividing both sides by m. You are right. Mass. Okay. That is it. So damping coefficient we got, and natural frequency we will get. Like natural frequency, we know that this we have already seen. Omega naught is equal to under root of k by m. Accordingly, we did some substitutions and we got this equation. So this is the differential equation for the damped oscillatory motion. So this equation describes the damped oscillatory motion with damping. Now if we look at the solution of this equation.
Sir, one second. Omega naught square is k by m.
Yeah, that is right.
The root you've taken to the other side. Okay, got it.
So omega naught is under root of k by m. So square we will do. That is one.
So just give me 1 minute, I'll write it.
Okay, right.
Done.
Okay. Now we will discuss the solution of this differential. So the solution of this differential equation will be the displacement, the function of the displacement, and that is what we are interested in. Ultimately, we are interested in that solution of the above differential equation. So we have the solution is something like x is equal to a naught e to the power of minus damping constant multiplied by t divided by 2l cos of omega t. Omega I will write because here omega is very important. The angular frequency, it will decide the nature of damping. Omega t plus phi is the phase constant. And here one very important thing, omega naught square should be greater than the square of damping coefficient. So for this condition, this is the equation of the displacement. Like normally in the normal motion, oscillatory motion, the displacement is a cos omega t plus phi. But here and there the amplitude was constant. But here this a naught is constant, but we know that in damped oscillation, amplitude is not constant. It is decreasing with time. This is the damping factor which is taking care of that fading.
Okay.
This is the mathematical formula for that.
Okay, so e to the power that is the damping constant.
Yeah, so damping coefficient. So e to the power of minus gamma t upon 2n. So this term we have to multiply with the amplitude. Because of that, with time, it is e to the power of minus something is 1 upon e to the power of something. And if the denominator decreases, the whole value decreases. So this entire thing, along with a naught, with time it will decrease.
Okay, sir.
With time it will decrease, isn't it?
Yes, sir.
So this is a very important displacement equation. This is the displacement equation for the damped oscillatory motion. I can call it the damping factor. Like this.
So can you write it down like which is constant and which is what?
The damping. And all other terms we are already aware that we have been seeing it from very starting. Omega, you know, it's the angular frequency. Small t is the time instance. Small m is the mass. Phi is the phase constant. And a naught is the amplitude. We can say that a naught is the initial amplitude. So this is very clear. Now, from this, one more thing we should take a note of, that is the angular frequency of damped oscillation. Because if I know the angular frequency, then I can get the time period also. Angular frequency damped oscillation. I can denote the angular frequency with omega. I do that. It will be equal to the root of natural frequency omega naught square minus the damping constant on 2m square. So this is the idea. So angular frequency of damped oscillation is under root of square of natural frequency of oscillation minus damping coefficient upon 2m square. And it is very clear that angular frequency of damped oscillation is less than the natural frequency, because natural frequency is omega naught and it is omega naught minus something. Omega naught minus something will always be less than omega naught. So angular frequency of damped oscillation is always less than the natural frequency. And here omega naught, we have already seen it is under root of k by n. And this note we can write it, very important. Damped angular frequency, which is the omega, is always less natural frequency. That is the omega naught itself. Now this angular frequency, it decides the nature of damping. So we have three types of damping: weak damping, heavy damping, and critical damping. And very quickly we will look at it, and it's important to just copy this equation. This equation will decide us. Based on this equation, we can have three types of damping that we will discuss now. So first, how we will do this. So we can do something here. I'm writing it now. So three types of damping we have to discuss: weak damping, then we have to discuss heavy damping, and finally we have to discuss critical damping. Okay. For weak damping, the condition is this. I am writing. For weak damping, this damping coefficient by 2m, it has to be less than omega naught. And when this condition will be satisfied, I can say that the omega will be real and positive. When this condition will be satisfied, I can say that omega, which is the angular frequency, will be real and positive. Why is it so?
Because the natural frequency is already higher. Naturally, because their mass they consider. No, mass doesn't play a role, right? Does it?
Omega, that is right. Omega will be real. See, just look at the under root. Omega will be real. See, the idea is that in under root, if omega naught is, if this quantity is greater than this quantity, then definitely inside under root we will have a positive number, no? Because in the under root, if we get a negative number, then it will not be a real number. It will be a complex number, because under root of negative is always a complex number. So since inside under root we will get a positive number, so the angular frequency will be real and positive. It has to be. Now this is clear. Now the next big question in front of us is that, okay, this is understood. How it will lead to weak damping? If the angular frequency is real and positive, then why we are calling it like weak damping? So weak damping means the damping will take place slowly. It is not that damping is taking place instantly. No, damping will take place slowly. So it is understood, because since angular frequency is real and positive, it will take some good amount of time for the decrease of amplitude to zero. So the damping will take place slowly, and hence it's a weak damping. And this is what we don't want. In like, let us suppose we have designed a car, and if that car experiences any sudden brake or a jerk or a we want that it should absorb the shock instantly.
But if it absorbs the shock instantly, then the damage will be high, right?
No. Like we will not experience the jerk, na? Like, or it will be a smooth ride. We say
talking for us, sir, for the parts of the car.
No parts of the car. We are talking for our comfort. Like all the luxury car we have now, like they have very good shock absorbers. The shock absorb. They absorb the shocks. What benefit we get is we say that, oh, it's a so smooth ride. And if you travel in a dabba car without any shock absorbers, and you
but auto would be a better example. No shock.
Yeah, auto. Just imagine if the road is having some potholes.
Yeah.
So there it is weak damping. Weak damping means if there is a shock wave, it will not get damped instantly. It will take time for it to damp. And hence we can absorb the earthquake also with some technologies.
Oh yeah. Like huge.
Because, like in the ground itself. Because see, earthquake, these are also waves, shock waves. So it can be damped with certain set of architecture. That is a different discussion, but idea is very clear. And earthquake is also weak damping, because if the earthquake wave originates, it is not that it instantly it fades. It travels a very long distance. It takes time for it to fade. To become its amplitude zero, it takes time. So that is a weak damping. So now we got a feel of it. And we also call it underdamped. Underdamped because damping is not taking place at the pace we want. The damping will be slow. And hence, out of anger, we say that, oh, it's underdamped. Now, let us look at the graph. And let me draw the graph, like I will copy. The 2-3 more properties we will discuss. So then we can look into the second type of damping. That vertical line. So we have this big damping graph. And very clearly we can see that in the weak damping, the amplitude is decreasing with time. It has to decrease with time. And with this equation, this damping factor is playing a role for this decrease. That is evident from the graph itself. And it is nearly sinusoidal, but exactly it is not sinusoidal, because progressively diminishing amplitude we can see in the graph. And here the angular frequency is near to the natural frequency in weak damping. So the idea is that if our angular frequency is close to the natural frequency, then we will exhibit the weak damping. And all the major examples we see around us, like pendulum, oscillating pendulum is an example of weak damping. Okay, and we have LCR circuit, inductance, capacitance, resistance circuit. So here we have electrical oscillations. So these are examples of weak damping systems. Now we will look at the heavy damping. Here, damping coefficient by 2m is greater than the natural frequency, because of which what will happen is this frequency, it will become imaginary. Because if the second term it becomes greater, so in the under root we will have negative. Okay. So the angular frequency will be imaginary. And what it states is that what is the significance of that? No oscillation at all. Omega will be imaginary. Because imaginary things does not exist. Imaginary things exist only in the dreams. and hence I can say that no oscillation at all. So heavy damping is so powerful. These are very strong shock absorbers. There will be no jerks at all, no oscillation at all, isn't it?
Yes.
And for heavy damping, the equation will become a bit different. The displacement equation, that let me write it properly, very important. Xt, like displacement at any point t is equal to C1 e to the power of minus gamma plus t plus C2 e to the power of minus gamma. And here what happens is that if a system is displaced from its mean position, it will return back to its mean position very slowly. It will not undergo any oscillation. It will not undergo any to and fro motion. It will return back to its mean position slowly. And once it returns back to its mean position, it will lose all its energy. So in heavy damping, to and fro motion is not possible at all. And hence we say that no oscillation at all. Like if we have a sponge, we press it and we see that after some time it will regain its shape. It will not oscillate. It will not oscillate like, okay, it will expand, then stretch, expand, stretch. That it will not do. And hence we call it heavy damping. Heavy damping we also called as overdamped. We call it overdamped. We call it overdamped. And here the damping increases with time. So one important observation I will make. Before that, let us make one graph, small graph. Then this topic will be. And like these are very important discussions we have to make. So with time, the body will reach its mean position, but it will take some significant time to reach there. So this is the time and this is the position, and it's heavily damped or over damped. And very important observation we have to make in this. Let us write it down. As damping increases with time, as damping increases, the time taken by the body to reach equilibrium increases. And it has got very good applications in real life. Very interesting applications we can see. We will discuss. You might have seen the doors of offices, the glass door offices in which AC air conditioning system is there.
Yeah.
So see, normal door, if you just push it, it shuts down instantly.
Yeah.
But there are doors which reaches their equilibrium position very slowly.
Oh yeah, soft close feature is there.
Yeah, soft close feature.
Yeah, and like because it's there. Yeah, I've heard about it. You just slowly like push it, it will automatically lock.
It will lock, but it will lock slowly. It will take some time because of this heavy damping.
Okay. Oh, okay.
So heavy damping is the reason for that. Because in heavy damping, what happens? Damping increases with time. So with time, it will slow down, and then like slowly, very slowly, it will reach its equilibrium. So heavy. Now the third scenario is the critical damping. So see, both the scenario we discussed, gamma by 2m is less than omega naught, gamma by 2m is greater than omega naught. Now the third situation is when both are equal. This is also very interesting to discuss. Like what will happen if both of them will become equal? Like gamma by 2m is equal to omega naught. What will happen? Then the applied frequency will become 0. Because if both will become equal, then we are subtracting both. So it will become 0. I will write it down.
Yes, sir.
I can also say it, or the damping coefficient will become 2m omega. In such scenario, we can see omega will be 0. And if omega is 0, then no oscillation. Because if angular frequency is 0, no frequency, no oscillation. No frequency, no oscillation. And hence we call it the critical damping. So what is the difference between heavy damping and critical damping? Because in heavy damping also there is no oscillation. In critical damping also there is no oscillation. The difference is the time taken to reach the mean position. In critical damping, we reach the mean position quickly.
Quickly,
yeah. Mean position or equilibrium position. Let me write it, equilibrium. Equilibrium position is reached quickly. Equilibrium position is reached quickly. Equilibrium position is reached quickly. And we need such kind of a thing in some electrical and mechanical systems. We need such kind of a behavior, wherein a quick return to the mean position without any oscillation. The idea is that if is displaced from its equilibrium position, it should instantly get back to its mean position without any delay. That is the idea. If I draw the graph, so it will be the time taken to reach the mean position will be less. So here in this graph, the time taken is more. In this graph, the time taken is less. X is equal to 0 means mean position. So with time, X is becoming close and close to 0. But here it is becoming 0 early. Time taken is less. But in the other graph, the time taken is more. This is only the difference between the both.
Okay, so main difference is mean position.
One example I can give you. In the keyboard also, the keys we type.
Mechanical keyboard.
Mechanical keyboard. Mechanical keyboard, the keys we type. You see that when I release the key, it instantly get back to its position. Just imagine if it would have taken time and I have to press B many times.
Yes, sir. Wait, I'll tell you something. Now they've changed it because like in competitive gaming, input time matters, right? So before they used to use mechanical keyboards where you cannot press two keys at the same time when you leave one. So now they have introduced optical, like there's this small laser going through. So that is much more quicker than mechanical. Yeah, but yeah, this principle is the same.
Principle is the same. So now you got an idea about advantage of critical damping.
Yeah.
Like many of the scenarios we need critical damping, isn't it?
Yes, sir.
And they have one more very interesting application. Let us discuss that. Critical damping. The application is the dead beat. Now, what is this dead beat? Let us look at it in detail. So we have seen meters like mechanical meters in the car also we have like mechanical speedometers in old car or the scooty or bike and all you see now the speedometer.
Yeah.
A circle dial clock like the speedometer and in that earlier we used to have meter reading also. There was a mechanical meter wherein the needle was there and needle used to fluctuate. Now we need that to be critical damping, especially in the speedometer. I keep on changing the speed. So if it takes time for it to reach to the normal position, then it will be inaccurate. That the measurements given by the speedometer will be inaccurate. We need a system wherein such kind of a delay shouldn't be there. Critical damping helps us there. And that we call as dead beat. Dead beat means instantly those needle, it will return to its equilibrium position without any delay. And like in physics lab, you might have seen galvanometer, voltmeter.
Yeah.
So there also we need this dead beat.
But then it will take certain time to reach there. Right?
Yeah, no. So that it will take once experiment is done and you have a galvanometer. Galvanometer is used to measure the current.
Yeah.
As long as you are passing the current, it is moving accurately. You are fluctuating the current, it will also fluctuate. But once you remove the current, then in order to reach its zero value, it will take some time, but that is tolerable. We are okay with that because now we are not interested. We have already done the experiment. But during the experiment, while we are observing that galvanometer, if we are fluctuating current, it should show us that current is increased, current decreased. It should not take delay. Otherwise, our experiment might go wrong.
Yeah.
Because we are also having a timer, stopwatch.
Yeah.
So it should show the reading instantly without any delay. So that dead beat is there.
Yeah.
And also the shock absorbers we have in the car or in the bike. There also there is no oscillation at all. The system it reaches its equilibrium position instantly. So there is a fluid. There is a fluid inside the shock absorbers, and that fluid can absorb the damping force. So this was critical damping.
Okay, sir.
Now, so like today we completed two different types of oscillation. Free oscillation, we got an idea.
And damped.
And damped oscillation is very important, and we looked into some output detail and also these three different types of damping.